We'll start the session now.
Recording in progress.
So today we'll go through all the topics we covered in this module. Then if time permits, I'll discuss the question paper for 21 intake. Right? And then we'll have the quiz on Wednesday. So I'll send the instructions for the quiz. You already know it's a closed book. 2 questions, 1 hour. So it will be at the lecture hall, usual lecture hall. And you have to bring your own paper to write, and whatever you need to attach the papers, right? So you need to bring those by yourself. Okay. So the module requires several background knowledge, which is from your previous semester subjects. So mainly the knowledge on LTI systems, Fourier analysis, and concepts like bandwidth. So these are for band limited signals. So we assume, right? So we assume you have all this knowledge prior taking the module. So there will be no direct questions from LTI systems or Fourier analysis. Right? So these are mainly, we expect you to utilize these techniques you learned in these modules when solving problems in this course. Right? So there will be no like direct LTI systems questions or Fourier calculation questions, but as a part of the solution, you may have to do all these things, right? A convolution, you may have to perform a convolution. You may have to perform a Fourier analysis. So those are required. Okay. So those things I didn't cover explicitly, right? So you have to know these things from your previous modules, and these will be utilized when solving the problems. So the first topic we did for this module was signal space, mainly representing L2 signals as vectors. L2 signals as a vectors. So L2 signals form a vector space. The idea was proposed by Kotelnikov. So he showed that L2 signals satisfies the requirements to form a vector space. So in addition to being a vector space, the inner product is defined on vectors for the signals, for L2 signals. So this forms basically an inner product space. So L2 signals can be represented as a vector in this signal space. So then we looked at the concept of basis functions. So if we can represent all the vectors, right? So basically as a linear combination of these basis vectors, so they basically span the vector space. So they form a basis for the vector space. As we discussed the importance of these basis functions in the process of communication transmitter design. So you can use the basis filters to represent, to simplify the transmitter mainly. Instead of having like large number of filters, we can only have the basis filters and use linear combinations of basis filters to generate whatever the signal in our signal space. So whatever we are transmitting is in the space space of the signals spanned by our basis filters. Right? So any signal spanned by our basis filters we can generate. So we always have a finite signal set, which can be represented as a linear combination of these basis vectors, so basis filters. We looked at how to generate signals using basis filters. We simply need to calculate these coefficients, and then we can represent any signal as a linear combination of these inner products and the basis filters. So that's the role of basis filters at the transmitter. Then we looked at the role of the basis filters at the receiver. So we showed that the best estimate we can have for an unknown signal is the projection of that signal on our space. So that's the best thing we can do. So that's the best approximation we can have for an unknown signal. With a communication system, we are receiving an unknown signal. So basically a perturbated version of our transmit signal. So we don't know the perturbation. It can be any random perturbation. So what we are receiving is basically a random signal or an unknown signal. So whatever we are receiving, the best we can do is we project it onto the space we know, and we get the projection. So that's the best approximation we can find in our known space for the unknown signal. So based on the projection, we use some distance measure. So later towards the course, we showed that we need to calculate, basically we are looking at the Euclidean distance. However, it's valid only for the case of IID Gaussian noise. So in the case of IID Gaussian noise, we check we basically measure the Euclidean distance between this projected version and our known signals. So that's valid only for the case of IID Gaussian noise. For other noise distributions, this may be a different metric. So the distance measure may be some other norm. So here it's a 2 norm. Maybe for some other distribution, it can be a P norm, right? So some general P norm. So from the signal space, we came up with the idea of constellations. That's a graphical representation of our signal set. So then we use that idea and the concept of randomness of the signal. And so the geometric representation and the randomness of the signals. By combining these two, we calculated the average energy of our signal set. So we saw that average energy of a signal set is equal to the moment of inertia of the shape formed by the signals in the signal space. So the average energy is equal to the moment of inertia of the signal set. So whatever the shape created by the signals in the signal space, then we can calculate the moment of inertia for that shape. So that will give you the average energy of the signal set. So in physics, we know the moment of inertia of a particular shape is minimized. That's when the axis of rotation is at the center of gravity. The origin is at the center of gravity. So using that concept, we showed that the average energy of the signal set is minimized when the center of gravity of that signal set is at the origin. Or simply, your signal set is symmetric around the origin. So we prove that symmetric signal sets, which are symmetric around the origin, have the minimum average energy. So if we are to check whether a particular signal set is the minimum energy configuration that can have for that signal set, you can simply calculate the center of gravity of that signal set and check whether it's at the origin. If the signal set, if the center of gravity of the signal set is at the origin, then that's the minimum energy configuration. If not, you can simply shift that, shift each signal to the center of gravity. Basically, you add the shift, right? You shift each signal so that the origin is now at the center of gravity. So the thing is, we simply shift the origin to the center of gravity, which means we have to give this shift to each signal. So once you give this shift to each signal, then the shifted signals will be the minimum energy configuration. So you can always find the minimum energy configuration. At first, you can find the center of gravity, and then you can shift each signal. Or basically shift the origin to that point, which is equivalent to shifting each signal by that vector. So that will give you the minimum energy configuration. Then we looked at the process of digital modulation. So the main goal of digital modulation is to come up with a bunch of waveforms, which are suitable to be transmitted over a given channel. So our source encoder gives us bit stream. So there can be manipulations for this bit stream. Some encryption may be added. So error control codes are added. So once you add all these things, you get the modified bit stream. So you need to transmit this using waveforms. So the process of converting this bit stream into waveforms is the digital modulation. So waveforms here, it's a finite number of waveforms. So we first group the bits and create symbols. Then we represent each symbol using an n-dimensional vector in the signal space. And then we assign a waveform to each signal. So we first looked at the baseband transmission. And we came up with this Nyquist criteria for ISI-free communications. And we saw that even in the absence of noise, there is ISI. The main reason is we don't have time-limited pulses. If our pulse is time-limited, then it will not be band-limited. So we cannot transmit it over a band-limited channel. So there will be ISI. So these pulses, they must satisfy some criteria to avoid ISI. So Nyquist first criteria gave that condition. Right? So condition, a pulse must satisfy to such that it can be used for ISI-free baseband communications. Right? So that was the Nyquist first criteria. So as long as the pulse satisfy Nyquist first criteria at the sampling instances, then we will not have ISI. And we don't care about any other time instance. We only care about the sampling instance. So in other instances, it can overlap. That's fine. But when you're sampling, there should be only one pulse active. All the other pulse must be zero. So that's Nyquist first criteria. We saw that the sync pulse and the rect pulse both satisfy Nyquist first criteria. So T-spaced sync, T-spaced sync, and T-spaced rect. So both satisfy Nyquist criteria. And T-spaced sync has the smallest bandwidth. It is equal to, if you want to send RB pulses per second, let's say r pulses per second, r pulses per second. We need at least bandwidth of r over 2 hertz. So this can be only achieved using the sync path. So r is 1 over t. So if you use t-space sync, then you can achieve a rate of r pulses per second to the bandwidth of r over 2. So this is the minimum bandwidth pulse required to maintain this pulse rate. So it's called the baud rate. So it's the pulse rate. So each pulse can represent one or more bits. However, both these pulses are practically, so they're not practically realizable. The rect pulse is practically realizable. However, due to the unlimited bandwidth of the rect pulse, the channel will distort the signal. Basically, it will spread the signal. So the pulse spreading again leads to ISM. So if there's a finite bandwidth channel, the rect pulse will lead to ISM. So sync pulse has a finite bandwidth. However, there's infinite duration, so which makes it impossible to generate. So if you truncate it, due to the large oscillations in the time domain, it has like large oscillations. These large oscillations again lead to very large bandwidth expansions. So more oscillations in the time domain means more bandwidth in the frequency domain. So this tells us if you are looking for a practically realizable pulse, you should look at a finite bandwidth pulse which has faster decay in the time domain. Faster decay in the time domain and smooth roll off in the frequency domain. And also we saw that by analyzing the Nyquist criteria in the frequency domain, we saw that the pulse need to satisfy this band edge odd symmetry. So band edge odd symmetry must be satisfied such that so the pulses they add up to this flat line. So to satisfy those requirements, we need to maintain this band edge odd symmetry and then the smooth roll off in the frequency domain. And also, it is preferred to have a rapid decaying pulse in the time domain. And also, we saw that the bandwidth of such a pulse is within r over 2 and r. Right? Where r is our symbol for pulse rate. Right? So to maintain a symbol rate of r, we need a minimum bandwidth of r over 2 and the maximum bandwidth of r. Right? We analyze these cases. We saw that whenever bandwidth is beyond RB or less than RB over 2, we cannot sustain ISI free communication. So all the practical pulses will have bandwidth excess of this R over 2. So R over 2 is the minimum bandwidth, or we call it the nominal bandwidth. So all practical pulses, they have bandwidth greater than R over 2 or the nominal bandwidth. So we call that the excess bandwidth. Excess bandwidth is the bandwidth above the nominal bandwidth. So larger the excess bandwidth, smooth decay in the frequency domain, which leads to rapid decay in the time domain. So we prefer to have more excess bandwidth in our pulses. Of course, it makes it less bandwidth efficient, but it makes your system more practical and also robust against synchronization errors. Like when you have very small oscillations, even if you even if you have like a timing offset when you're sampling, if you have an offset at your sampling instance, still you can have very good communications. But if you have very large side lobes or very large oscillations, you make a small error in the timing, so that will lead to large contributions from other pulses. So we require our pulses to have sufficiently large excess band. So the ratio between the excess bandwidth and the nominal bandwidth is called the roll-off. The roll-off and the total bandwidth is simply R over 2 plus your excess band. So that's the total bandwidth usage. So you can, right? So you should be able to design pulses for a given requirement. If you are to maintain this particular symbol rate at this band, right? What is the modulation scheme you need to pick? Right? Basically, you need to figure out how many bits per symbol you need to put. Right? So because the channel puts a limit on the symbol rate or the pulse rate, not the bit rate. So it puts a limit on the pulse rate. So then you can decide what type of modulation to use. Then you can maintain the required bit rate. We saw that practically these Nyquist pulses are mainly they are from the race cosine family. So the total response of your transmit pulse and the receive pulse or the receive filter must be race cosine, or simply like this one pulse. So we saw that when we go ahead with a large excess bandwidth pulse, we are using more bandwidth. 100% excess pulse uses the maximum bandwidth of RB or R. So that's 100% more than the minimum band. So it's wasting spectral resources. So to overcome that, we looked at the controlled ISI concept. So instead of having zero ISI, we introduce some controlled ISI so that we can reduce our bandwidth usage. So we try to introduce some known ISI so that we can recover. If we can recover, since we know the all possible ISI patterns, according to that we can come up with a detector, decoding algorithm. Then we can reverse the impact of that ISI. The control ISI allowed us to transmit. Basically, you can transmit a rate of R pulses per second with a bandwidth of R over 2. Okay, so there's a question. So does the channel limit the pulse rate and not the bit rate? Yes. The channel puts a limitation on how fast we can transmit the pulses. Right? I mean channel bandwidth. Right? Of course, channel puts a limit on the rate when it comes to SNR. So that's if you talk about the Shannon capacity. So Nyquist analyzed the impact of channel bandwidth. So channel bandwidth puts a restriction on the signaling rate. how fast we can signal. How fast we can signal. So basically, SNR puts a limit on the information rate. So if you take applied information theory, you will learn more about this. Right? So the concept of entropy. Right? So how to map the so gain bandwidth will be a function there as well, and SNR and the rate. So Nyquist talks about the right. So you basically the pulse bandwidth. Right? So you need at least that much of bandwidth to maintain that pulse rate. If the bandwidth is less than that, you cannot sustain that rate. So that's the idea of Nyquist theory. So you can increase the pulse rate using this duobinary. We looked at Nyquist second criteria and you can higher data rate, have a higher data rate with a given bandwidth using duobinary pulses. However, we saw that there's a possibility of error propagation because your current decision depends on your previous decision due to the ISI. Again, I think I mentioned this when we talked about our detectors. We talked about our optimal detectors, so that a detector is optimal when we detect symbol by symbol, when there's no ISI. Whenever there's ISI, memory is involved. So you cannot do symbol by symbol detection. So you have to use these trellis-based decoders. So whenever ISI is there, it's not a symbol estimation, it's a sequence estimation. So if you are to, right, so in theory, they have proved the optimal strategy for sequence estimation, right? MLSC, maximum likelihood sequence estimation. So this achieved using the Viterbi algorithm. Right? But here we don't have to use Viterbi because ISI is with only one symbol. But when you have large ISI or large channel memories, we have to use this sequence estimation. Right? Or we have to use a very complex equalizer and get rid of the ISI and then pass the equalized signal for symbol by symbol decoding. Well, that's the proper way of communication because especially in a wireless channel, there will be always ISI. And if you look at like a GSM signal, it has a very low bandwidth, like 200 kilohertz. But if you look at modern signals like 4G, 5G, the channel bandwidths are like 100 megahertz. So you can, pulse rates are very large, right? Signaling rates are very large. So this leads to lots of ISI when it comes to multipath channels. And so you must use a very complex equalizer, or you had used schemes like OFD. So that's why most modern systems, 4G or like wireless LANs, they use this OFDM instead of single carrier modulations. So you can learn about this semester 5, I believe, semester 5 or 7. I think semester 5 also we cover some parts. So whenever there's ISI, you cannot do symbol by symbol decoding. It's always related to previous decisions. So you have to use sequence estimations. So with controlled ISI also, we have that problem to a certain limit. However, since the ISI patterns are known, we can easily correct those. However, if we make an error, that error will propagate. So to overcome that, we introduce a precoding technique. We came up with a precoding technique, and then we came up with a new decoding rule for that precoded signals, and we showed that once you pre-code it, that correlation between the data is removed. Right? So we can do that as well, right? If we know the ISI beforehand, we can pre-code our data so that ISI will be pre-cancelled. So ISI is pre-cancelled. Before transmission, you process your data such that ISI is not affected. Right? So in OFDM, this use something called cyclic prefix. So cyclic prefix is simply to, so we know the signal will be affected by ISI. So we add the cyclic prefix so that channel, it's okay even this part is destroyed. So that's the whole purpose, right? So we add the cyclic prefix such that it can be destroyed by the channel so that our data is protected. So it's some sort of pre-code, not exactly pre-coding. So some sort of like we are doing something before transmission to minimize the effect of ISI. So we do this pre-coding to pre-cancel the ISI, and then we can recover our data without correlation among the previous signals. Then we looked at equalization. So when there's a channel, multipath channel is involved, so there's a channel memory involved. So in a cable, of course, you can figure out the memory comes from capacitance and inductance. Both are storing energy, capacitance, inductance, right? They store energy, so that means there's memory. But in a wireless channel, memory comes from multipath propagation. So all the channels, practical channels, they have memory. So we need to use these equalizers to reverse that. And so equalizers are also, right, so designed as tap delay lines. So tap delay lines simply try to reverse that memory introduced by the channel. And we looked at the zero forcing equalizer, where you try to zero the ISI, try to fully cancel the ISI. However, we saw that we cannot do it for all the time instances. So we can only do it for a limited time range. So we pick the severe ISI region, and then we apply zero forcing equalizer for the for the severe ISI regime, and we get this low ISI signal. So you can design the equalizer to satisfy either Nyquist 1 or Nyquist 2. Equalizer simply invert the channel. It's a channel inversion equalizer or a zero forcing equalizer. So there are more complex equalizers. However, we didn't go through that. Okay. Then we looked at passband systems. We looked at this spectral wastage. Spectral wastage of first we looked at the need for passband. Because we cannot sustain baseband communications always, especially when it comes to wireless. Wireless systems must be passband if you want to have multiple communication systems in the same location, or if you need multiple users in the same location. So, and also to have reasonable antenna sizes and to utilize the frequency diversity in our channel responses, we prefer to use passband communications. And then we looked at when we have a real baseband signal, when it comes to passband, we are wasting like half of our band because our communication signals are real. So if the signal is real, it must have this conjugate symmetry. So when you have a real baseband signal, to maintain the symmetry, right? So the spectrum usage doubles in the passband. So that motivates us to use a complex baseband signal and then construct a real passband signal. Yes. So instead of using a real baseband, we can create a complex baseband so that we utilize all the spectrum instead of wasting it like in the real baseband signal case. So when it comes to complex baseband, now we are utilizing all this bandwidth, right? So there's no bandwidth saving. There's no bandwidth saving. Basically, we are utilizing all the bandwidth. Right? You saw that, right? When we analyze the spectral efficiency, HAM and QAM has the same spectral efficiency in passband. Spectral efficiency is same. So we are not saving bandwidth, but we are utilizing it. So, and also the advantage is you get power efficiency because now you're adding another dimension. Right? So you have in-phase and quadrature carriers carrying two baseband signals. So that's the advantage of complex baseband signals. As we discussed QAM. So there's no baseband QAM, it's always passband. So QAM is always passband. So schemes like PSK is also simply a QAM scheme where the signals have the same amplitude. And then we looked at the performance metrics. Performance metrics, we discussed the power efficiency, spectral efficiency, and error probability. So we defined some, so we came up with some definitions so that we can make sense of these things, right? Things like Shannon bandwidth, dimensions per second, pairs of dimensions per second. So things like that we define so that we can connect all these things. N naught over 2, noise energy per dimension, spectral efficiency, bits per pair of dimensions, bandwidth. So we discussed all these concepts so that we can connect, we can make connections. So utilizing this, we came up with this detection methods. So the detection rule, we use this maximum a posteriori probability rule. So you make an observation, and then you pick the input which is most likely to make this observation. So maximum likelihood, what we do is we take each input and calculate the likelihood of producing that particular observation. In map rule, you take the observation and you calculate the probability. This could have been SK. This probability, this could have been SK. Probability of SK giving this particular output. Right? So maximum likelihood is given SK is transmitted, what is the probability of receiving this particular value? So these two are different. So we saw that for the special case of equiprobable signals, these two are equal. When you have equiprobable signals, map is equal to ML, and in the presence of IID Gaussian noise, we have the minimum distance detection. So using the minimum distance detection, we came up with the distance-based decision regions for each signal. We simply find the locus of the equidistant points between the signals, and we consider the intersection of all these equidistant point lines. Right? So based on that, we figured out the decision boundary for each signal. Right? So we only consider the two-dimensional case. So we came up with these expressions to calculate the probability mass within these regions. Right? So whenever the signal remains within the assigned region, your decision is correct. Right? So you can calculate the probability of that event by calculating the probability mass within the region. So sometimes this is simple, sometimes it's difficult, sometimes it's impossible to calculate this probability mass. And also, you should be able to like rotate and see whether you can convert it into a, like a convenient calculation. Because we learned that IID Gaussian noise is rotationally invariant. And when the noise is IID across all dimensions, we only need to worry about the noise energy, not the noise orientation. So it's only valid for IID Gaussian. Only IID Gaussian noise is circularly symmetric or rotationally invariant. Because it comes from the joint distribution, not individual distribution. So using the Gaussian Q function, this rotational invariant of the noise properties, we can evaluate these probability masses in this decision region. We can calculate the error probability for each signal, and then we can calculate the average error probability. So when we are talking about an average, talking about the error probability, we are talking about the average symbol error probability. Because we are transmitting a symbol, not a bit. Right? So bit error probability is different from symbol error probability. We saw that there's a connection when we have gray encoding. Otherwise, we cannot define a good connection between symbol error probability and bit error probability for memory modulation. We discussed the Gaussian Q function. Basically, it's the CCDF, complementary CDF of a standard normal random variable. So QX gives you the tail probability of a standard normal random variable. It's the tail probability. So this part is 1 minus 6, right? And also you have, so this part is 0.5. So this part is x, and this QX. So this part is simply what? This part is 1 minus 0.5 plus QX. Right? So this may also be useful sometime. And the relationship between QX and the error function, ERF, another function related to the Q function is called the error function. We may use the Q function, but these older softwares, they have error function, not the Q function. Old MATLAB versions, they have the error function, not the Q function. So you can calculate these error probabilities using the Q function. And we saw that most of the modulations, we can approximate the error probability using this expression, where B is known as the asymptotic, so BO2 is known as the asymptotic power efficient. So basically, we call it like that because it simply scales your energy. The higher the B, the lower energy you need to maintain a certain error probability. So B is a measure of energy efficiency or the power efficiency of your modulation. So we analyze the power efficiencies and spectral efficiencies of different modulations. We compared them. We saw that QAM is superior in terms of power efficiency compared to PAM and PSK. And also we discussed about FSK, the special case of FSK, called orthogonal frequency shift key, where the frequencies are orthogonal to each other. So the orthogonal frequencies, to maintain the orthogonality, you need to make sure the frequency difference is set to 1 over 2t, where t is the symbol duration. So FSK can be implemented as a direct passband scheme or a baseband to passband. That's also fine. So for each symbol, you generate a pulse, right? Then you multiply the carrier with this pulse so that the carrier only exists for the pulse duration. Okay, so that is also possible. So FSK can be direct to passband. You simply map each symbol to a orthogonal carrier, or you can have these pulses. Then you can multiply the pulse with an orthogonal carrier. We saw that FSK behaves opposite manner to our PAM, QAM, and PSK. So with FSK or orthogonal FSK, you need more frequency when you increase the bits per symbol. When you increase the signal set, you need more band. But with all the other modulations, when you increase bits per symbol, you need less band. However, there is PAM, QAM, and PSK becomes less power efficient when you have large signal sets. But for FSK, the power efficiency increases with them. So we learned that this is due to the use of higher dimension. So more dimensions you have, you can spread your signals, or basically you can increase the distance between the signals more using the same amount of energy. So you can spread the signals across multiple dimensions to increase the distance between the signals with a limited energy. So that's the whole idea of this FSK. It's a higher dimensional signal. It's spectrally inefficient. But in terms of power, it's more efficient. So you can select modulations where you are bandwidth critical. If it's a bandwidth critical application, then you can go ahead with a scheme like a QA. If it's a power critical application, then you can go with a scheme like FSK. It's like a low rate communication system. Right? You can use FS. Like second generation cellular, GSM. So GSM used FS. Okay, it's a very low rate communication. It's a lower rate communication. And modern systems, they use multiple modulation types. So depending on the channel conditions, they will change the modulation size and the power levels. Because modern systems, they use adaptive modulation, adaptive transmission. So that is to make use of this like opportunistic, utilize the channel opportunistically. And whenever the channel is good, you try to send more bits, more throughput. So okay, the question is the difference between FSK and OFSK. In OFSK, so we know in FSK, for each you map it to a different carrier. So that's FSK. So these carriers, in different ways. So general FSK is this. So in OFSK, what we have is to take the product between the carriers is almost zero. So that is OFSK. So in OFSK, if you want to have M signals, right, OFSK, you need M dimensions. Because each carrier is orthogonal, which means each signal is orthogonal. So M signals is dimension. Right? So all these are bases. All these carriers are bases. They form a basis for the signals. There can be other FSK schemes, like we discussed this and say minimum shift. So minimum shifting the minimum possible gap between these frequencies, like MSK. And we have GMSK. GMSK uses a Gaussian pulse, and minimum like MSK. Pulse is GM, so that's what it is being used. So right here, there are so many FSK schemes. Right? Uses orthogonal carriers. Right? Basically, it forms the basis for FDM master. So FDM is a form of orthogonal FSK. So OFD. So beauty of OFDM is you can encode signals using, then you can transmit them using OFD. You learn these things, right? So how to implement it. It's a very flexible regulation. You can use PSK or whatever to do the signal encoding. Then you can transmit it using FSK. So that's the difference, right? So basically how we calculate this frequency gap. So depending on how we calculate this gap, there are different FSK schemes.
Recording stopped. Recording in progress.
Okay, I got disconnected. I don't know how much you heard. So I assume you are okay with the answer. If it is not clear, you can ask again. So many different FSK schemes are ways we can set this frequency gap. Right? We saw that OFSK is spectrally inefficient. Spectrally inefficient is more power efficient. It's higher dimension. So other schemes may not have like higher dimensions like OFSK. So basically, this FSK is quite similar to FM, frequency modulation. Right? So if you look like you have studied FM, and if you implement, like if you apply a pulse stream to a frequency modulator, what you get is a FSK signal. FSK is simply frequency modulation with a digital signal. So that's the basic definition for FSK. So different form of FSK are there. And you know, like so that you have that integral relationship. That phase the integral. It has some smoothing effect. So there's a rapid frequency changes, rapid phase shifts are avoided with this FSK. And we discussed that differential modulations and offset modulations. So to avoid that sudden frequency shifts, The FSK has that ability inherently because the phase is the integral of the signal. You have learned FF. So there are extreme versions of this, like CPM, continuous phase modulation. We discussed this, so they are used in very simple devices. And so there are so many things, so many more things to learn in this digital communication. And what we did was a very basic introductory course. Like so there's no limit. There's so many things you can learn. So what I covered was a very introductory version of digital communication. If you're interested, you can take the semester 7 or 8 as another module. I think it was not offered in all these years because nobody took it. And of course, it's a little bit difficult. So if you go to higher, like advanced courses of digital communication, it's very difficult. It's hard. These courses are very hard. You need a lot of knowledge on random processes. So of course we can do it if sufficient number of students are taking it. We can mainly cover all these advanced topics. Okay. So finally, we looked at receiver implementation, how to implement the minimum distance detector in actual hardware, using the correlator or the match filter approach. And we showed that match filter simply maximizes the output signal to noise ratio. So for a given signal set, and you can figure out the basis. You can figure out the basis functions, and then you can figure out the match filter as well, and match filter receiver as well. So then also you can calculate this and now, and you should be able to do these things. So that's why I said in the beginning, you should be able to calculate a convolution, right? So the Fourier transforms, right? Because so noise is involved. Noise also goes through the filter. So you have to apply the Parseval's theorem, and, right? So to calculate the noise power. So those things, so those are background knowledge. And this error probability also I mentioned this. So you can ignore these Q squared terms. You can approximate it using a Q term, and then you utilize like the parameter B as the power efficiency. So regarding the exam, so it will be a 3-hour exam with 4 questions. So 3 from the parts I covered and 1 from Professor Taraka's part. Total 4 questions, 3 hours. So mostly analytical questions. There'll be no of course explanations are required, like explain why these two are different, right? That type of things you should know. So today I don't think we have time to discuss the questions, so we can do it on Friday. So we'll have the quiz on Wednesday. So this is mandatory. Right? There's no alternatives. Right? There'll be no alternative quizzes for this. So it's mandatory. And please bring your own paper so that you can write. And so we'll cover questions from digital modulations and this performance metrics, match filters, right? So that type of things. So mainly what we studied from digital modulation. Okay, so we'll stop here. So I'll send an email regarding the quiz. Right? So nothing to worry. So if you have gone through the lectures and if you have attended the tutorials, should be it shouldn't be a big issue. Okay, so we'll stop here.